In this video, I'm going to go ahead and take a Physics 1 exam for a job that I need to do. And as a result, I'm going to show you how I go through the solutions. So that's today on High Peak Education. What's going on, everybody? I hope you are having a great day. So I have to take this for a job that I'm doing, and so I figure I might as well just go ahead and record myself taking this proficiency exam, and then you'll get a chance to see how I think about these Physics 1 problems. Remember, Physics 1 is sometimes called AP Physics or college-based Physics 1. Some of these problems will certainly include some mathematics, some geometry, some trigonometry, and there might even be some calculus. So we're going to take a look at that, and let's go ahead and get started with today's content. So here we have a question where we have a car going over the top of a hill, and it looks like this hill is in the shape of a semicircle, that is a half circle, and we know, let's see, the car has a mass of 573 kilograms. It's traveling over the top of the hill, as shown in the figure. The hill has a radius of curvature of 32 meters. What is the speed required to make the car leave the ground at the top of the hill? So what speed is required so that the car will for sure leave the ground at the top of the hill? Okay, so a couple things to look at here. First of all, this R here is what they mean by the radius of curvature. So that's the 32 meters. We know the mass of the car, but I think we're actually going to see here that we're not going to need it to do the calculation. It won't be required. And I think we'll see why in just a moment. We want the speed required to make the car leave the ground. So let's think about conceptually, physically, what's happening when the car leaves the ground. The car is going to project off the top of the hill. You could imagine that the car is going fast enough where it no longer retains contact with the hill. Now, why would a car do that? Well, you can imagine when we go fast enough that the car no longer retains contact with the hill because it actually has very little force between itself and the ground. So it will leave the ground and project off the hill if the force between the ground and the car is gone to zero. That force we often call the normal force. Some of you may have learned it as the so-called support force, but you could call it the normal force. And this normal force between the ground and the car has to go to zero at the top of the car's motion in this half circle path. Now notice this car, even if it's moving at a constant speed, has to have a net force on it. Now how do I know that? Well, it's because the car is changing its direction. Because it changes its direction, when we have a force, that can be due to a change in speed or a change in direction. Because force, that is a net force, comes from an acceleration, which again is a change in either speed or direction. In this case, even if the car were to come up the hill at that constant speed we're about to calculate, it would project away from the ground. If the normal force goes to zero, the entire time it has to have a net force that holds it in towards the center, which we call the centripetal force. But if you think about it, the centripetal force is always present on the front side of the hill until it gets to the top of the hill. When the car gets to the top of the hill, the normal force must go to zero in order for it to project away from the hill, and the only force that's on the car that's producing the net force is the weight. On the front end of the hill, we have both the weight and the normal force, but then when we get to the top of the hill, we only have the weight. The normal force becomes zero. And you may say, well, what about the actual centripetal force? Well, ladies and gentlemen, one thing that you hopefully have learned is that centripetal force is not an actual force like the other force types. Centripetal force is another way to manifest the idea of a net force. Something else must manifest itself as the centripetal force. And in this case, only the weight will manifest itself. So at the top of the hill, the centripetal force, that's the net force, must manifest itself as the weight. So we come up with the following equation at the top of the hill. The centripetal force is equal to the weight. Now the question is, how could you start to get this in actual physical quantities so that you can calculate? Well, the centripetal force, hopefully you recall, that's mv squared over r, where m is the mass, v is the speed, we square it, and divide by the radius of curvature. And what is the weight? Well, that's just mg, as long as we assume the acceleration due to gravity is constant. So we come up with exactly this equation. And here's an interesting thing. I kind of mentioned this before. We're given the mass of the car, but do you notice that the mass appears on both sides of this equation? So in fact, it will cancel. Another way of saying this is that this problem is independent of mass. So think about this. If you have more mass, sure, you have greater centripetal force. But if you have more mass, there's more weight. And the net effect doesn't really matter. It goes away. So this calculation is not going to depend upon what the m is. So right now we have v squared over r equal to g. And this is pretty straightforward algebra to solve for v. I think I just need to multiply by r and take the square root. So we're going to assume that this speed is positive. So when I take the square root, I'll only take the principal square root. That is the positive square root. So we end up with the square root of rg. And I think that we can just put the numbers in. So let's go ahead and just do that. That's going to be v equals to the square root of, let's see, r was 32 meters. G we know to be for Earth approximately 9.8 or even 9.81, but I think we can just safely use 9.8 meters per second squared. So using our calculator, let's generate our answer using the square root of 32 times 9.8. And we get about 17.7. Now, throughout this exam, we're going to try our best to look at significant digits. It's also useful to look at the answer choices. But 17.7 is about 3 significant digits. The radius of curvature was 32. The mass of the car given was 3 significant digits. So I'm going to round this to 3 significant digits. So v being 17.7 meters per second, that looks like it's the third choice down. So I'm going to go with the third choice down, consider this problem correct, and we'll move on. Okay, question 2. 2 blocks labeled A and B are sliding without friction toward a frictionless ramp. Block A has a mass of m, speed 2v. Block B has a mass 2m, speed v. Which block will slide the furthest distance up the ramp? Now, there's no mention that these 2 blocks are going to interact. So I'm going to assume no collision between these blocks. I mean, otherwise it'd be sort of obvious because block A would collide with block B, and block B would sort of like generally go higher just because it's further along. I think the question is asking about if each of them in a separate experiment were cast with the mass m versus 2m, that's block A versus block B, with velocity 2v versus v, which is going to attain a higher distance up the ramp. Now think about this. Both of these blocks have the same momentum. Hopefully you can realize that, linear momentum. Block A would be 2mv. Block B would also be 2mv because they have a 2 and then an mv when we multiply, so they have the same momentum. But do they have the same kinetic energy? And the answer is they do not. Now, you might think about forces in a case like this, but I think it's going to be much easier to analyze in terms of energy. How do I know that? Because we're talking about masses and velocities. We don't necessarily want to have to calculate accelerations or forces or free body diagrams if we can avoid it, because mass and velocity are the inputs to the kinetic energy, the energy of motion. So I think that energy considerations will be a much better way to analyze this problem. Let's go ahead and calculate the differences here. So which block has greater kinetic energy? So let's look at the kinetic energy of block A versus the kinetic energy of block B. Now for block A, we go 1/2 times its mass, that's its m, and then times its velocity, that's 2v squared. Notice its velocity is 2v, whatever v happens to be. V itself could be 1 meter per second, could be 10 meters per second, but it's just 2 times whatever that v is. We're going to go versus the kinetic energy of block B is 1/2, but we've now got a 2m for the mass. It's twice as massive, but the velocity is just v squared. Well, when we calculate this out, I square the 2 here, that's going to be a factor of 4. 4 times 1/2 is 2. And then we go mv squared. And then that's going to be versus, now here, 2 times 1/2 is just a factor of 1. So that's just going to be mv squared. So I believe that indeed, this has twice the kinetic energy that this does. So in fact, block A will attain twice the height of block B, because if you looked at the conservation of energy equation, you would look at the fact that, at least in its most general form, the kinetic energy initial would equal the gravitational potential energy final. So that's like 1/2 mv initial squared equals mgh final. Now notice these masses cancel. The problem is independent of mass, and the h final, the final height that these things attain, depends on the initial velocity squared, and we divide by 2g. So indeed, objects with the larger initial velocity will go higher than objects with a smaller initial velocity. Another way of saying this is that this has a larger kinetic energy than this, that's block A, has a larger initial kinetic energy than block B. So it will indeed go up higher, further distance up the ramp. So I'm certainly going to go with block A and consider that correct, and let us move on. Okay, so here we have a problem, question 3, that says the graph shows how the position of a particle depends on time as it moves on the x-axis. Which choice is closest to the average speed of the particle in the time interval between 0 and 6 seconds? Because this is a position versus time graph, I'm going to consider the vertical axis like x, and then the horizontal axis like t. So when we think about average speed, hopefully you know, is the change in position over change in time. So this is the equation for average speed, right? The bar notation here means average. This is change in position over change in time, delta x divided by delta t. Now the question is, what interval do we do this over? Well, I think we're told it's between 0 and 6 seconds that we perform this change. So the 0 to 6 seconds, I think, should go from the left-hand end of this graph, that's over here at 0, to this point right here, because we have a grid. So 1, 2, 3, 4, 5, that's about 6 seconds right there. So what we should do is we should locate those 2 points. So that's 0, 40 for the first point, and it looks like this is 6, now it's hard to say exactly, but I'm going to suggest that's, actually 25. So this would be 25, 30, 35, 40, because I think each of these vertical grid box increments is 5 meters. So this is the point 6, 25 meters. Okay, so when we calculate this average velocity, we can say this is change in x, so that's 25 meters at the end, minus 40 meters at the beginning. divided by 6 minus 0 seconds. So that's about negative 15 meters divided by 6. So negative 15 divided by 6 is going to give us equal to negative 2.5 meters per second. So that should be roughly the average velocity over this interval. Now we are asked to calculate the average speed. So the average speed would be the magnitude of the average velocity to give us speed. Technically, what I wrote up here, this was velocity because that has direction associated with it. Notice the displacement was negative. That is to say the particle's moving to the left on the x-axis. Another way to see that is you could draw a secant line slope. Remember, the secant line is not the tangent line. It's the line which has a slope between 2 points. That's the average rate of change of the position versus time. Now, by the way, you could also estimate this from the graph. I think it's a little harder to do, so I think it was easier to use the numbers. Sorry, if I take the magnitude of this, I get about approximately 2.5 meters per second. Now, I don't see an exact number like that, but I'd say what's closest is about 2.2 meters per second. Now, I think that that's pretty good because if you look, remember where my dot was? I think the actual curve was just a little bit above this 25 mark. So this should be more like 27 minus 40. So that means this magnitude is going to be a little bit smaller. So I think 2.22 meters per second or so is probably about right for the average speed of this particle. Okay, so I think that is good. We have finished this problem, and I'll consider question 3 done. Let us move on. Okay, now question 4. A stone is thrown at an angle of theta equals to 45 degrees above the horizontal x-axis near the surface of the Earth with an initial speed v0. If air resistance is negligible, which of the following v versus t graphs best represents vx versus t and vy versus t? And notice we've got lots of choices. We've got 5 different graphs and lots of combinations. So I'm going to suggest that the best way to solve this problem is to predict what we expect Vx versus t to look like, and then likewise in a moment Vy versus t. Now Vx versus t, that should be the instantaneous x velocity versus time. That is to say the horizontal velocity as time moves forward. What do we expect that to look like? Well, air resistance we're told is negligible. So what that means is we have what kind of motion? Okay, projectile motion. Hopefully you remember in projectile motion, in the absence of air resistance, it's constant velocity in the x direction and constant acceleration in the y direction. That is to say, horizontally, in the absence of any outside forces like air resistance, the stone will continue to move horizontally to the right with a positive x velocity that does not change. Graph number 3 is going to indeed be Vx versus t because it's positive, it's unchanging, and it just stays a nice constant positive x velocity. Okay, so it's just this flat graph, and that's what we expect. All right, how about Vy versus t when air resistance is negligible in this projectile motion? Well, this is going to take a little more explaining. So Vy versus t is going to be constant acceleration downward due to gravity acceleration. So when the stone is thrown upward, we start off with a positive y velocity. But when the stone reaches its maximal height, the y velocity is 0. And then when the stone comes down, the y velocity is becoming negative. Another way to say this is it goes up, then it stops going up, and then it comes down. So it's positive vertical velocity, then 0 vertical velocity, then negative vertical velocity. So what graph looks like that? That's going to be this one, graph number 5. That's Vy versus t. Also note that the slope of this graph is constant, So it's a slope that is negative and constant. And in fact, the value of that slope is going to be approximately negative 9.8 meters per second squared. Because you could imagine that the velocity change over time is going to be about the value for Earth's gravity acceleration. And if the direction is downward, that is negative, we put a negative on it. So negative 9.8 meters per second squared, about negative g. So we need to look for the choice that has Vx is graph 3, but then Vy is graph 5. So I'm thinking that's this final choice. So they tried to hide it as the last choice. Vx is graph 3, Vy is graph 5. Okay, so I'm going to consider that this question is done, and then we'll move on. So here we have a simple harmonic oscillator problem for question number 5, and a solid block of mass m on a massless spring with spring constant k oscillates back and forth between x equals negative a and x equals positive a, and assume there's no friction between the block and the table. The oscillator has a maximum speed v. What is the amplitude of the oscillation? Now in this problem we're also given that, recall, for a simple harmonic oscillator, omega is equal to the square root of k over m. So we see the setup here, we see k, we see m, we see negative a, 0, positive a, we see an x-axis, and then we see the choices. Okay, so a couple things to say as we get going here. First of all, when we have a mass m with an ideal spring and there's no friction, we're going to assume simple harmonic motion. We're also told it's a simple harmonic oscillator. So what that means exactly is that the force is exactly proportional to the displacement. That is, when x is positive, the restoring force of the spring is negative, and when x is negative, the restoring force of the spring is positive. This thing should oscillate as a simple harmonic oscillator. You could imagine that the wave on a position versus time graph should look like either like a cosine wave or a sine wave, something very nicely plotted. If that's all the case, we can just go ahead and solve this problem by considering what's the equation for the maximum speed v compared to the amplitude a of the oscillation, and how is it related to omega? Okay, so let's assume that this mass starts its oscillation at positive a, that is, when it's maximally elongated at its positive amplitude. Hopefully you recall that the position versus time function would be exactly x of t equals a cosine omega t, where a is the amplitude, cosine function, and then omega is the angular frequency. That's what's shown right here. Now the angular frequency has units of radians per second. Now a lot of teachers just call that 1 over seconds, but I don't think that's all that helpful, because that would be like the same units to some extent as regular frequency as opposed to angular frequency. Furthermore, inside a cosine or a sine function, usually we want this phase, that is what's inside the parentheses, to be in units of radians. So let's think about this in units of radians per second. Now we get units of radians per second by taking newtons per meter, that's the spring constant k, divided by mass, which is in kilograms. So we end up with units of kilograms canceling out, and then 1 over seconds squared, you did a square root, you just get 1 over seconds. But again, radians are sort of unitless, so that's going to be radians per second. Time, of course, is going to be in seconds for the SI unit, so that means this is indeed the function that we have. Now, if you recall, we can derive a very similar expression. I'm assuming the phase shift is 0. In other words, this oscillator starts at its maximum value for x. So that way it's just a nice pure cosine wave. No horizontal phase shifts on the position versus time graph. We can get a velocity versus time function out of this pretty easily. And that's going to exactly be v of t equals negative omega a sine omega t, where v means velocity. The reason it's negative is because the velocity will be in the opposite direction compared to this position graph. I mean, think about this, right? When x is positive, in other words, this thing's elongated, it's going to end up moving left eventually, like at least when we release it at time t equals 0. So that's why we have a negative here. Hopefully many of you that are my calculus viewers also know that v of t is the time derivative of the position function. So if I take the time derivative of this using your calculus 1 skills, the derivative of cosine omega t is negative sine, but by the chain rule, an omega comes out the front. Now, hopefully you can realize from this that we can pretty easily look at essentially the amplitude of the velocity function and get the maximum velocity. So that is v max, the maximum velocity magnitude, or you could just say the maximum speed, is equal to omega times a. Now, by the way, we're also told that's equal to v in this problem, but we're also told that omega is equal to the square root of k over m. So we end up with the square root of k over m times a, that's the amplitude, is equal to v. But for the final answer, we're looking for what is the amplitude of the oscillation. So we then need to solve this for a. So in order to do that, we have to multiply by the reciprocal of this square root. So indeed, what we'll just get is a, which is the amplitude, is equal to v, which is the maximum speed, times the square root of m over k, m being the mass, k being the spring constant. And notice that's exactly the first choice here. So notice the v is not tucked under the square root. That's why this is incorrect. And it's not any of the other choices where you'd have to be careful. It is going to be that first choice where it's v times the square root of m over k. Hope that makes sense, and let's move on. So here we have a basic orbital mechanics problem in physics. Question 6. A small planet mass m is moving in a circular orbit radius r about a star of mass capital M. Derive the formula for the kinetic energy 1/2 mv squared, that's lowercase m, that's the mass of the planet, as a function of r. So in other words, the kinetic energy is equal to what? Question mark. Well, let's think about what we need to do. First of all, we know that we've got a 1/2. Secondly, we've got m, that's the mass of the planet, but we need to figure out an equation for v, because we need to get the velocity, well, really the speed, that this planet moves as a function of r, and we want to see how that is going to give us a final answer in terms of r, in terms of radius. Well, hopefully one thing that your teachers have shown you in your Physics 1 course is this is basically going to be the derivation for orbit velocity. What do I mean by orbit velocity? So orbit velocity comes from the fact that when this planet is orbiting around this star, you could think of the only force that holds the planet in the orbit is the universal gravitational force, which is directed toward the center of the star from the center of the planet. And because it's being held in circular motion, the net force is indeed just the centripetal force. So indeed, for orbit velocity, the universal gravitational force is exactly equal to the centripetal force. Let's see what that looks like in terms of equations. So we have F subscript capital G, so that's the universal gravity force, equals F sub c, that's the centripetal force. And notice we get Newton's universal law of gravity. So we're assuming Newtonian gravity here. We're not having Mr. Einstein enter the room right now. So we just have G, capital G, lowercase m, big M, over r squared, because that's the universal gravity force between the planet and the star, lowercase m being the planet, capital M being the star. the radius between them, well, it's r, but then r squared's in the equation. And then that equals the centripetal force. So if you recall, that's mv squared over r. Notice we did have to use lowercase m because it's the star that's actually rotating around. Notice that two simplifications can occur immediately. One is, I hope you note that this mass of the planet immediately cancels. And it turns out one of the radii will also cancel. Now, just one of them. So, in terms of the algebra, we have v squared equals g capital M over r. But then taking the square root, we have v equals the square root of gm over r, where I brought the g up, I applied the square root. And so this is what we know to be orbit velocity. But we can either use this orbit velocity equation in here in the kinetic energy equation, or just use this equation for v squared. In fact, I think the v squared is going to work even better. So this v squared equation can go right in here for this v squared. And what do we get for the kinetic energy? We just get that the kinetic energy is equal to 1/2 lowercase m times, now v squared is just big G capital M over r. So let's clean this up in terms of the terms. Let's put the 2r in the denominator because they multiply, and then big G out front, capital M, and then lowercase m, just so it looks like one of the answer choices. Or sorry, just this third choice down, I meant to say. Just this third choice down is big G, capital M, lowercase m over 2r. And that should be the equation for the kinetic energy. So the kinetic energy, it turns out, is actually half of the magnitude of the universal gravitational potential energy. Now that's kind of a mouthful, but hopefully you recall the universal gravitational potential energy would be like negative G capital M lowercase m just over r. Not over r squared, just over r. And if you remember, it's negative because it's bound. Remember, when a planet is bound to a star, then it can't realize its own potential energy on its own. And then half the magnitude of that is indeed just this. So that's something interesting we find from basic orbital mechanics energy. So I hope that makes sense. And let's consider question 6 complete and we'll move on. Okay, for question 7, a ball with mass 9.4 kilograms is thrown up at a 86.3 degree angle above the horizontal. The ball initially has a velocity of 46.4 meters per second and starts approximately on the ground. How long is the ball in the air before it hits the ground? So this is a projectile motion problem. How do I know this? So if we assume that there's no air resistance. Now there's no mention of air resistance in this problem, so we have to assume that it's 0 because we're not given any additional information about how to calculate air resistance either. So we can say that the x components are independent from the y components. If you recall, in projectile motion, we know that it's constant velocity in the x direction and constant acceleration in the y direction. And in fact, in the x direction, it's just constant motion, no forces. In the y direction, it's just free fall. So because it's just free fall in the y direction, we don't need the mass of the ball, but we can just determine the time that it's in the air from kinematics only in the y direction. So what we need is we need the y initial velocity. We're not going to worry so much about the x kinematic variables. The final y velocity is not so important. It's just going to be the opposite of the initial y velocity. We know what the total displacement is going to be. That's going to be 0. And we also know that the time is what we're looking for, and we know what the acceleration is. It's negative g. So let's start writing these kinematic variables down. So Vy initial is going to be, now it's going to be the y component. Because it's launched at an angle, that's going to be like V initial times the sine of theta initial. Hopefully you see how I got that. Vy final, it's just going to be the negative of this, so it's no more information. We don't really need to use that. Delta y, that's the total y displacement, should be 0 meters because we start and end at the ground. Okay, so then the time is what we're looking for, so we'll put a question mark there, and the acceleration in the y direction should be negative g, or at least it's approximately negative 9.8 meters per second squared near the Earth's surface. Okay, so how are we going to know which kinematic equation to choose? Well, it comes from the ignored kinematic variable. So the ignored variable is the y final velocity, because if you think about it, we don't really gain any additional information. So the kinematic equation I'm thinking about is the vertical free fall displacement curve. Namely, delta y is equal to Vy initial times t minus 1/2 gt squared. Now remember, g is a positive number as here, but it's a minus in the equation right there in this term because it's directed downward. Well, we can go ahead and put some numbers in and really start thinking about this. So Vy initial is Vo sine theta initial times t, and this is going to be minus 4.9. Now how do I got that? Because it's 1/2 times 9.8, so minus 4.9. T squared is equal to 0, because delta y is 0. I just kind of changed sides on the equation. But hopefully you notice this is exactly a quadratic equation. And this is a quadratic equation such that we can factor out a t. Now, why do we want to factor out a t? So first of all, we can avoid using the quadratic formula. Secondly, we can clearly determine what time is the later time that it reaches the ground. In fact, if you factor out a t right here, you have negative 4.9 t, let's see, plus Vo sine theta initial. Close out the parenthesis equal to 0. Now notice we have two separate times. This first time here, this is at the start of the motion. That is when time is exactly equal to 0. But we're not interested in that time. We are interested in this time because this is the time later that it reaches the ground. So we can just solve that equation pretty easily for t. So negative 4.9 t plus V0 sine theta initial is equal to 0. And if I move the 4.9 t over with a plus and divide by 4.9, then you just get t equals Vo sine theta initial over 4.9. Now, by the way, 4.9, again, that's just the same thing as 1/2 g. You could have just kept that as 1/2 g. But, you know, so if you were deriving this, like the teacher wanted this all in terms of variables, then it'd be like this, 2Vo sine theta initial over g, because dividing by 1/2, something's multiplying by 2. But anyway, let's go ahead and put the numbers in. So I think we have just this. So it'd be 2 times the initial velocity, which was 46.4 meters per second. We're going to multiply that by the sine of the angle. That's sine of 86.3 degrees. And then let's divide that by g. So divide that by 9.8 meters per second squared. Okay, so we need the calculator for this, at least to efficiently calculate it. Okay, so let's go fraction, and then let's go 2 times 46.4 times, and I want to make sure my calculator is in degree mode, which it is. That's good, because I want this angle in degrees. So I need to multiply that by the sine of 86.3 degrees, close it off, and divide by the acceleration due to gravity. So that's 9.8 meters per second squared, close to Earth's surface. So we get about 9.45. So this is about 9.45 seconds. So that's about how long the ball is in the air. Now notice That's because we shoot it almost directly upward. 86.3 degrees is almost a vertical shot. It's a little bit off from vertical, but it's in the air for a long time. So 9.45 seconds is the fifth choice. So I'm going to consider that for the correct answer, and then we'll move on. Okay, question 8. Which object experiences the greatest net torque? 3 objects, a solid sphere, a hoop, and a cylinder, all have the same mass and same radius. Starting from rest, all 3 are released at the top of a ramp as shown in the figure. They begin to roll down the ramp without slipping. Which object experiences the greatest net torque? Now, I think this question's a little tricky, and we want to really nail it down. In order to nail it down, I'm going to suggest that we use the following free body diagram. Now, by the way, I did not draw this free body diagram myself, but it is nicely colorized, nicely shown in terms of how it works. And I want to make a couple comments on it. Notice the free body diagram, though, has sort of the inclined plane facing the other direction, at least compared to what's pictured, but the essence of it is exactly the same. So here we have the free body diagram. Notice, again, it's just a reversed mirror image of what we see here in the diagram, where instead of sloping down from left to right, we slope down from right to left. But effectively, it means the same thing. By the way, this is going to be the same free body diagram for any of the shapes, as we will see here momentarily. Okay, so whether the hoop, sphere, or cylinder, imagine this is a side view profile, and let's call the positive x direction parallel to the inclined plane. That makes the positive y direction perpendicular to the inclined plane. Let's assume the angle of the incline is theta, and hopefully you know from the geometry that if theta is the angle of the incline, that's also the same thing as the angle between straight down towards the center of the earth and perpendicular to the inclined plane. That's because this right here is 90 degrees minus theta, and this would be the complementary angle, namely it'd be theta degrees as well. So that's important. Notice, let's define the positive omega direction as counterclockwise as viewed from our profile direction. That's the positive direction as this thing rolls for the angular velocity. And that's going to also be the same direction for the positive torque, as we'll see. Okay, so let's start analyzing the forces. So there's really just 3 forces on this free body diagram. What are they? So notice the normal force is on the center of mass. That's called C. And notice the normal force comes from the contact point, but it's on and through the center of mass, such that the normal force goes perpendicular to the inclined plane. That's shown here in the red vector, and it's labeled capital N. Pretty straightforward. The weight is given by mg, of course. So the mass times the gravity acceleration near the Earth's surface. Notice, though, that this weight, which is shown towards the center of the Earth as a downward green vector, can be split up into 2 components. Namely, the component that's parallel to the inclined plane and the component that's perpendicular to the inclined plane. The part of the weight that brings us down the inclined plane would be mg sine theta, whereas the component that pushes into the inclined plane is going to be mg cosine theta. Now, how do I know that? Well, if you consider this right triangle here that I'm tracing with the pencil, notice that the opposite, that's across from theta, is indeed the sine component across from theta, whereas this component here, which by the way is the exact same size as the normal force, is mg cosine theta. So indeed, the normal force is mg cosine theta, and then the part of the weight that's bringing us down the inclined plane is mg sine theta. Hope that all makes sense. But what we're most interested for in this problem, because we're going to roll without slipping, is the friction force. Now this friction force technically is going to be the static friction force. Now some of you may be very upset when I say that, because you may say, wait a minute, this thing is moving, why is there a static friction force? I know. But this point, P, that's in contact between the rolling object and the ramp is momentarily at rest. Hopefully you've analyzed that before. Think about this. It's momentarily at rest when it's in contact. So the only reason that there is any torque on this object is because there's a static friction force here. Note that the weight and the normal force are both at the center of mass. And since the axis of rotation is at the center of mass, in the geometrical center of any of these rolling objects, there can be no torque about the center of mass from the normal force and the weight, because the radius out to the normal force and the weight is both zero. There's no lever arm. So any forces on the axis of rotation will always be zero torque. But notice the friction force is not only at point P, but it's also perpendicular to the radius, which we label capital R, but it's also providing a torque, which is actually what causes this thing to create a rotational acceleration. So there's only a net torque due to the fact that the friction force, the static friction force, is not acting at the center of mass, and it's at this radius r. Okay, I hope that kind of makes sense. Now, the torque is going to be given by the static friction force times the radius. How do I know that? So hopefully you know that torque is r times F times sine of phi. Many of you have probably learned this. Torque is tau, r is the radius, which I'm going to put in as capital R in just a moment. F, the force, is the friction force, that's lowercase f. And then the angle between them, what's the angle between this radius and then this friction force? Well, that's 90 degrees. So we're going to have capital R times script cursive lowercase f times sine of 90 degrees. But we know this is the radius, this is the friction force. Sine of 90 degrees is exactly 1. Now the friction force should be given by the normal force times the coefficient of static friction. So indeed, this torque is going to end up becoming R times mu s times the normal force, which is mg cosine theta. We already went over that. But wait a second, let's think about this carefully. The radius is the same for all objects, because they all have the same radius, but we're all told they have the same mass. Let's assume the static coefficient of friction is the same for all objects, because they're all on the same surface. And let's assume the angle theta, of course, is the same for all the objects, because they're on the same ramp. But if that's the case, then the torque should be the same for all the objects. Now, some of you may be really troubled by this answer and me coming up with this last choice here as the correct answer, all experiencing the same torque. Because many of you have probably analyzed this problem or a very similar problem and said that if the three of them are given a race, in other words, they're all released at the same time, that the sphere wins the race. In other words, it gets down to the bottom of the inclined plane first, whereas the hoop gets down the latest. In other words, it takes the most amount of time. And that's true. But even though they have the same torque, they all don't have the same rotational inertia. So hopefully you recall that another way to write torque is rotational inertia times angular acceleration, alpha. So even though these are all the same, we know that the eye of the hoop is the largest, so it's going to have the smallest angular acceleration, whereas it's going to be the smallest rotational inertia, capital I, for the sphere, and that means the angular acceleration of the sphere is actually greatest. And that's why the sphere actually makes it to the bottom of the incline most quickly. Now, that's because the torque is the same, but the rotational masses is not the same because the rotational inertias are not the same, given that they're different shaped objects with different rotational inertias, and their mass is distributed differently with radius. So the one with the largest angular acceleration, the sphere, will indeed reach the bottom first, and then the hoop with the smallest angular acceleration will reach the bottom of the incline last. And the cylinder is going to be somewhere in the middle. That's because the hoop has the largest amount of mass all at the edge, so it has the largest rotational inertia, whereas the sphere has some on the edge, but a lot in the center of mass, whereas the cylinder is kind of in between. So a hoop is mr squared for the rotational inertia, a cylinder is 1/2 mr squared, whereas a sphere is 2/5 mr squared. So hopefully you've seen those equations before. But indeed, they all still do experience the same torque. So I consider this kind of a difficult question, but hopefully we've got this. Hope that makes sense. For question 8, let us move on. Question 9. A rocket is launched straight up, and the net force in the rocket as a function of time is shown in this graph. The rocket travels straight up, defined to be positive here, between time equal to 1 hour and time equal to 3 hours. What happens to the speed of the rocket? Well, look what's happening. We're looking at the net force versus time. So the net force looks positive the whole time to me, certainly between 1 and 3 hours. And what that means is it should be accelerating, because if the net force is in the direction that the object's already moving, and positive is upward and it's a positive net force, this thing should be accelerating. It should be speeding up the whole time. So indeed, that's the choice we're just going to go with. So it's not slowing down, it's not moving at a constant speed, and it's not speeding up for a while then slowing down. That would be a positive net force and a negative net force. So I'm just going to go with the first choice, and I think that's all we need to do. This is a pretty quick one. Hope question 9 makes sense. Okay, so here we have question 10. 3 blocks are connected by massless strings and massless frictionless pulleys as shown. The middle mass, m sub b, is on a frictionless table, and it's observed to be sliding to the left with constant speed. What are the correct relationships between the magnitudes of the tensions and the magnitudes of the weights? Okay, so a couple thoughts as we kind of get going here. So first of all, if we're moving at a constant velocity, that means the net force must be 0. Now, because these are all attached to one another, given what's called the acceleration constraint, that means all the objects must be moving at a constant velocity. In fact, the acceleration must be 0 for all of them, which also means via Newton's second law that the net force must be 0 for all of these objects. We note that tension 2 and tension 3 must be the same magnitude. How do I know that? Well, the only way we can move at a constant velocity is if mb has 2 equal size but opposite direction forces on it. By the way, let's not worry about the vertical direction on mass in the middle on the table, mb, because the weight and the normal force would just cancel out one another, whether there was friction or not, whether it's accelerating or not. So, yeah, I mean, tension 2 and tension 3, though, horizontally, must be the same magnitude. It's the only way the velocity is constant. So we're already thinking about the following choices, either second or fourth choice. Now, the question is, what about here? Is the weight of m subscript a greater than tension 1 or equal to tension 1? And then the same sort of thing with m sub c. These all have to be accelerating together. We already talked about this. So if they're all accelerating together and they're all moving at the same velocity, then we know that we're not getting any net force or net acceleration. So indeed, if you looked at the free body diagram here on m subscript a, the weight down and the tension force up must be equal size, opposite in direction, for there to be no net force. So indeed, we have this for the correct choice. Now, one last thing. In this particular very special case, tension 1 and tension 2 have to be the same as one another. Now, why is that? Well, this pulley is massless and frictionless, so all the pulley does is redirect this tension force. So tension 1 and tension 2 would have to be the same, as long as this is a massless, frictionless pulley. So even if the system is accelerating, T1 and T2 would be the same. Now, if the system that was accelerating, T3 and T4 would be the same as well as one another, but T2 would be larger than T3 in order to accelerate it. But, in fact, all the tensions, and even MA and MC, have to be the same mass as one another, thus the same weight, and equal to these tension forces. Otherwise, the system is not going to move at a constant velocity. Okay, so this indeed has to be the case. Okay, this is a very special case of, this is kind of like a classic Physics 1 problem, so I hope that makes sense. And as always, let me know. I appreciate your feedback, but hopefully that makes sense. Let's move on. Let's take a look at question 11. It says, consider the inclined plane shown. A wheel of radius 0.20 meters is mounted on a frictionless horizontal axle through its geometric center. A massless cord is wrapped around the wheel and attached to an object mass 0.20 kilograms that slides on a frictionless surface inclined at theta equals 20 degrees with the horizontal as shown. The object accelerates down the incline at 2.0 meters per second squared. What is the value in kilograms times meters squared of the rotational inertia of the wheel about its axis of rotation? Okay, so in order to do this problem, here's what we have to consider. There's a connection between the linear variables and the rotational variables. Okay, so how are we going to relate these things together? How are we going to rotate the rotation of the wheel with the mass that's sliding down? We need to say that in the absence of friction, that we could either analyze this in terms of forces and rotational forces or in terms of energy. I think forces is probably going to be the best way. And the torque, remember, is like force times the radius, should equal to the tangential force, this is a tangential force, times the radius for the wheel. Let's think about this torque. Torque is the same thing as rotational force, but that's rotational mass times rotational acceleration. So that's going to be moment of inertia, that's capital I, times angular acceleration, that's alpha. Now, by the way, we're looking for the rotational inertia, by the way, so that's the question mark. So we want to find this. Now, the tangential force is the same thing as the tension force. So I'm just going to call that capital T for the tension force. And we multiply that by the radius. Now the question is, how can we get this tension force? Don't think it's just the force only that brings this mass down the inclined plane. That's because we need to do a little free body diagram for this mass. So this mass has the portion of the weight that goes down the inclined plane. That's mg sine theta. I'm not going to cover where that is derived from in this problem. Hopefully you've seen that before. That's the parallel to the inclined plane portion for a mass that's sliding on an inclined plane which is elevated at angle theta above the horizontal. But the tension force is what holds the mass back, so I'm going to call that T. And if we look at the x direction for the mass m, then let's call this the positive x direction. You would say that mg sine theta is positive in the x direction minus the tension is equal to, according to Newton's second law, mass times acceleration. So we can solve this for the tension force by saying mg sine theta minus ma equals the tension force. So that can get substituted into this expression right here for this T, this tension. One other thing, we don't know what the angular acceleration of the pulley is, that is, of this wheel, But we know alpha is that angular acceleration. By the way, because you could think about this torque as more like the net torque. It's what actually causes it to accelerate in terms of its rotation. But the way to relate angular acceleration to linear acceleration is through alpha equals a over r. How do we get that? Well, if alpha is in radians per second squared, a, the acceleration, the linear acceleration, is meters per second squared. You divide by meters, you get 1 over second squared, which is really, because radians is unitless, radians per second squared. So this is how we relate rotational to linear quantities. So that gets substituted into here. So what does this equation become? So I'm just going to call this star for a second, and then star becomes what? So it's I, which is the rotational inertia, we're looking for that, times A over R equals, and then the tension force becomes mg sine theta minus ma, I'll put that in parentheses, times R. Okay, and then I think what we need to do is we need to multiply by the radius r and divide by the acceleration a. So that means I, the rotational inertia, would be like mg sine theta minus ma over a, because we divided by a, but we're going to multiply also by r, so this is going to be r squared. Now notice also that the mass m is common to both of these, so we could kind of clean this up a little bit by factoring out a mass m, and then I could even split this fraction up by going g sine theta over a, so that's g sine theta over a, and then I factored out the m, but then a over a is just 1. This is just minus 1. So that's a little bit easier to plug into, if you will. Okay, so let's in fact put the numbers in. Okay, so let's put the numbers in carefully. We need the mass, which is sliding down, that's m. That's 0.2 kilograms. So we're going to go 0.2 times the radius, but squared. So that's 0.2, this is meters, squared, and then I'm going to go parenthesis, and then I'm going to go fraction, then I'm going to go g sine theta, so that's 9.8 times the sine of theta, now theta was 20 degrees, and that's going to be over a, which is 2.0 meters per second squared, and then just minus 1. Close off parentheses, enter. I being about 0.0054, and that's kilogram meters squared. Well, let's see which choice that is. It's right here. Okay, so it's the third choice down. So I'm going to assume that's the correct answer. Hopefully this analysis makes sense. Let's move on. Okay, question 12. This is a vectors question, clearly. Which of the following statements is true about vectors A, B, C, and D? And they're all vectors. So it looks like we've got some relationships here. Now, in a lot of these cases, it's either A plus B, or A plus C, or A minus B. Okay, so let's maybe think about starting here in the lower right corner. So if I start in the lower right corner, A plus B gets me to this ending spot. If I start and I end here, that to me looks like vector A plus vector B. Now how do we add vectors? We add vectors tip to tail. So what that means is the tip of A we pick up with the tail of B. So we go in the direction of vector A, and then we start going vector B. Okay, so that's like vector A plus vector B. Looks like it's... Now, look at this. I'm going the wrong direction on vector D. So if I go this way, but then I add vector C, I end up in the same spot. So that's like negative vector D plus vector C. But then the question is, which of these is this most closely related to? And I'm actually thinking it's probably the second one, because subtracting a vector is the same thing as adding its negative. So that's vector A plus vector B is equal to vector C minus vector D. Okay, so I think that'd be the correct choice. Hopefully that makes sense. There's other ways you could do this. You could also say, if you wanted to start and end at the same spot, you could be like A plus B. So I'm going around this direction, and then we're going the wrong direction on C, so that'd be minus vector C. But then it'd be plus vector D, because you would go this direction, still going back to the starting point, and that gives you 0, because you end and you start in the same spot. But then that's still going to also, once again, get back to this equation. Okay, so I hope that makes sense. Let's move on. Question 13. An object of mass 2 kilograms moves at constant speed, 0.5 meters per second, along a path as shown. What is the magnitude of the momentum change? Magnitude, that's absolute value sign, delta P, when the object travels from point A to point B. If the object's moving at a constant speed, 0.5 meters per second, that means this is 0.5 meters per second only in the y direction, and then this at point B is 0.5 meters per second in the x direction. Now be careful though. We note that it's actually the negative x direction for point B. And the momentum change, remember, momentum's a vector, but then we need to take the magnitude at the end. So the change in the momentum should be the same thing as the change in the momentum in the x direction plus the change in the momentum in the y direction. Now the question is, how do we add these up? Well, these are along separate axes. So really, the magnitude of the momentum change is going to be the Pythagorean sum of these. It's going to be the square root of the x momentum change squared plus the y momentum change squared, and then added up and square rooted. That's because the momentum change is going to be, sorry about that, to the left and down. Why is that? Well, in the negative x direction, the negative y direction, we lose y momentum, but we gain negative x momentum. So that's why it's like this. So this is the direction of the vector. Okay, so how are we going to get the change in the x momentum? Do you notice that the x momentum is non-zero at point B, but it's 0 at point A. So I think that the change in the x momentum is just the mass times the Vx final, but then again, we have to square that. But then for the change in the y momentum, we have to go 0, which is the final momentum, minus the original. So that's minus mvy initial. Okay, and then square that. Okay, now the mass is 2 kilograms in these cases. The x final momentum is negative, or x final velocity is negative 0.5 meters per second. And then again, we have to square this. Plus, again, negative 2 kilograms, and then times 0.5 meters per second. And then we have to square that, and then the square root. 2 times a half is just 1. So this is just negative 1 squared. That's just 1. Plus, and this is negative 2 times a half, which is negative 1, squared is just 1. And the square root of this is the square root of 2. And the square root of 2, so this is just the magnitude of this vector. So the magnitude of this vector is like adding these things up and taking the square root, because we want the size of this thing. Otherwise, we would just keep each of them in separate coordinate components. But the square root of 2 is about 1.41. So that's going to be about this. And the units of momentum change are kilogram meters per second. So I'm going to go with the fifth choice. And I believe that's the correct answer. Hope that makes sense. Let's move on. It says a treasure chest filled with gold has a mass of 450 kilograms and is sitting at the bottom of the ocean in a place that is 6.6 meters deep. A chain is attached to the treasure chest. The treasure chest can be pulled up to the surface. Since the treasure chest is filled with gold, assume that the chest has the density of gold. Assume the ocean water has the density of regular ocean water. What force is required to lift the treasure chest? Okay, so a couple thoughts as we kind of get going here. So first off, what are we given? That the treasure chest has a mass of 450 kilograms. So MC, so C just means chest, is 450 kilograms. It's sitting at the bottom of the ocean where the depth, so let's call that H, is 6.6 meters. A chain is attached to the treasure chest. Now let's pause for a second. Chains are typically heavy, so we usually need to take into account the volume that the chain takes up and the mass of the chain. Now we're not given any information about the mass of the chain, so we're going to assume that the chain is thin and insignificant in terms of mass. So I'm going to ignore the effect of the chain. We're going to assume that the treasure chest has the density of gold. Now density, typically you use the symbol rho. Now hopefully you know from the periodic table that the density, the chemical symbol, is Au for gold. So I had to take a second to look this up, but the density of gold appears to be about 19,300 kilograms per meter cubed. Now, don't let that throw you, some of you who are really into chemistry. If you were doing this in chemistry units, that'd be about 19.3 grams per centimeter cubed. Okay, so in physics, we use SI units, which is kilograms and cubic meters. We also know that it's being lifted out of regular water, so the density of water is 1,000 kilograms per meter cubed. That's a number that you probably should have memorized, because that's 1 gram per centimeter cubed. That's exactly how we set the metric system. Okay, so the question is, what is the force required to lift the treasure chest? Let's see what's going on with the treasure chest. Let's model the treasure chest like this. And hopefully you're aware that required to lift the treasure chest, that's like the tension. Okay, so this is tension, and the tension goes up like this. That's T. But the question is, what force or forces are also on this treasure chest? Well, it certainly has its own weight, so that's mg, okay? And then this is m subscript c, it's the mass of the chest times g. Remember, the chest is filled with gold. But then, what other force is helping us because we're below the water? So hopefully you're aware of this. It's the buoyancy force, Fb. So the buoyancy force from Archimedes' principle is equal to the weight of the displaced fluid. So that means the tension plus the buoyancy force has to be greater than or equal to. So in other words, to just barely get it to pull upward and overcome this weight, it has to be greater than the weight. And again, this is the weight of the chest. Now, let's solve this for the tension force, and then let's put in the expression for the weight of the chest, mc times g. And let's start talking about the buoyancy force. So tension greater than or equal to the weight of the chest is mcg. The buoyancy force is the weight of the fluid displaced. So it's going to be the mass of the water displaced times g. Now, how do we get the mass of the water displaced? Well, the mass of the water displaced, that's kind of hard to do, but it's going to be like the exact same shape as the treasure chest, but this is just water. And we usually can't take that water, put it on a scale, so instead we say mass is just density times volume. So that's the density of the water times the volume of the water displaced. But look at this. This is very important. Make sure you understand this. As long as this chest is sealed and it's airtight and no water is taken into the chest, we assume that the volume of the water displaced is exactly equal to the volume of the chest. Hopefully you're aware of that, right? Like, if you put yourself down in the bathtub like Archimedes did, the volume of your body should equal to the volume of the water pushed out of the way, right? Same thing when you get in a swimming pool. And that's just water displacement. So we say that we need to find the volume of the chest. Okay, so let's write this out a little more. Tension greater than or equal to mass of the chest, G, and then it's minus the density of water times the volume of the chest times G. Now, how are we going to get the volume of the chest? Well, volume is like related to density. I've already been using the fact that density is mass divided by volume. But if I want the volume of the chest, I need to take the density of gold, and the mass of the chest is here, and I can rearrange this. So the volume of the chest via algebra is mass of the chest divided by the density of gold. So see how I did that? I multiplied by the volume of the chest, then I divided by the density of gold, and that's going to go in here. So I'm going to need to go on to another page. So we've got tension greater than or equal to mass of the chest, G, minus, now density of water is here, but then the volume of the chest becomes mass of the chest divided by the density of gold. So it's mass of the chest divided by the density of gold. And then don't forget, we still have a G there. And then now I think we can plug everything in. In order to plug everything in a little more nicely, you see that the mass of the chest times G is repeated. So this is MC G. And then if I factor that out, we have 1 minus the density of water divided by the density of gold. Now notice, this is kind of an interesting thing. Do you see that the tension is going to be smaller than it would be if the object were not in water? Because you're going to do 1 minus something, and that something is related to the density of water compared to the density of gold. Kind of interesting, right? And this is where you get into the idea of what's sometimes called reduced gravity, or basically there's a weight reduction, if you will, due to the buoyancy force. Okay, so let's get this calculated. The tension is greater than or equal to the mass of the chest was given as 450 kilograms. G, we always know, close to the surface of the Earth, it's about 9.8 meters per second squared. Then we're going to go 1 minus, now the density of water we know to be 1,000 kilograms per meter cubed. And the density of gold, we looked that up earlier, 19,300. 19,300 kilograms per meter cubed. So let's get this tension and use the calculator. So 450 times 9.8, okay, that's this front part, parenthesis, then let's go 1 minus, and then we'll go fraction bar 1,000 over 19,300, and then close the parenthesis off. Okay, so we've got 4,182 or so. So it's 4,182 newtons. Now, if the tension is larger than that, clearly we can accelerate the chest upward. If it's anything less than that, we don't have enough force to pull the chest upward. But I said it's 4,182, so it looks like it's the third choice down. Does that make sense? Okay, I hope so. So 4,182. Hope that makes sense. Again, this is an Archimedes principle buoyancy force question. Hope that makes sense for question 14. Let's move on. Question 15. You are standing on a very low friction skateboard, initially at rest. A friend throws a heavy ball at you. What should you do in order to acquire the greatest speed? Catch the ball, hit the ball back at your friend, same final speed whether you catch the ball or hit it back. So this is a change in momentum problem, and hopefully you're aware that the correct answer is you should hit the ball back to your friend. Now, why is this? So there's a couple ways to think about this. First of all, if you catch the ball, that's an inelastic collision. If you hit the ball back, it's an elastic collision. Now, an elastic collision, at least in a pure sense, conserves kinetic energy, whereas an inelastic collision, energy is lost in the collision due to heat, crumpling, sound, things like that. Another way to think about this is that in elastic, that is bouncing collisions like this, the change in momentum is a much larger vector directional change, whereas for inelastic collisions, where the objects stick together, the momentum change is only in the same direction, so there's not as much of a vector direction change. Here's one last way to think about it, and this is just intuitively. If I stand on the skateboard and I hit it back, the idea is that I'm pushing off the ball to propel myself more quickly. If I catch the ball, my mass goes up. And if my mass goes up, then it's harder to move me. And as a result, I don't have as much of a speed change and momentum change. So indeed, based on one of those intuitive arguments, I hope that you know you should hit the ball back to your friend. Okay, hope that makes sense. Let's move on. Question 16. A mass m is on the end of a spring and is oscillating back and forth between negative a and a as shown in the figure. When the mass is at position O, or 0, and moving to the right, the acceleration of the mass is what? Well, when you're at position O, I think that x equals 0 at this moment. And hopefully most of you know that the only force in a simple harmonic motion system where a mass is on a frictionless horizontal surface attached to an ideal spring is going to be the Hooke's law spring force, is minus kx. But if x is 0, then this should be equal to 0 newtons right now. And if the spring force is 0 newtons, that means the acceleration should equal to 0 meters per second squared. So it is going to be 0. Now you may say, why does the object keep moving through the equilibrium position right in the middle? Because it has inertia, because it has velocity, because it has kinetic energy. So the only reason the mass keeps passing through the equilibrium position is due to Newton's first law, inertia. But it doesn't have a force on it at the moment. After it moves past equilibrium, it'll gain a negative force to the left, which after it's elongated, it'll bring it back towards equilibrium. And when it's compressed, the force will always be to the right in the positive x direction. Hope that makes sense. 0 net force right now, such that we have 0 acceleration at this moment. So now question 17. Two air carts are initially at rest on parallel tracks. Cart A has twice the mass of cart B. The same force is applied to both carts for the same amount of time. After that time, what can we say about the magnitude of the momenta of the two carts? Okay, so this is a question which really tests your ability to understand the change in momentum. It's the same force applied to both carts the same amount of time. So what that means is F delta T is the same, and that's the same impulse. Remember, impulse is force times time, but it's also equal to the change in momentum. So both of these carts gain the same amount of momentum. Since they were both initially at rest, they should have the same momentum as one another. Now you may say, wait a second, cart A is more massive than cart B. I agree. But even though cart A is more massive than cart B, they will have the same momentum because they have the same change in momentum. What the situation will actually look like is cart A will be moving faster than cart B. In fact, cart A, being twice as massive, should be moving half the speed of cart B, but they should have the same momentum because we push with the same force over the same time period. Does that make sense? So the results of what you view will not look the same, but they will have the same momentum. Okay, I hope that makes sense. Question 18. If you stood on a planet which has twice the mass as great as Earth, and a diameter which is also twice as great, you would weigh how much? So for Earth, hopefully you know to calculate the gravity acceleration constant, that's like taking Newton's universal gravitational force law and dividing by your mass to get your local acceleration. And we use not only the mass of the Earth, but the Earth mean radius on the surface. So this is going to be like g, mass of the Earth, divided by the radius of the Earth, squared. And again, we know this is about 9.8 or so meters per second squared. Now let's talk about this new planet. Let's call it planet X. So what's the g for planet X? First of all, it's twice as massive. So we go g, 2 times Earth's mass. But listen to this. It has a diameter that's twice as great. But 2 times the diameter means 2 times the radius, because the radius is just half the diameter. So I think that this is going to be 2 Earth radii squared down here. Now let's work out these proportionality constants. This is 2g, mass of the Earth, over, then when you square this 2, you get 4, radius of the Earth, squared. But 2 over 4 is a half, times g, times the mass of the Earth, over the radius of the Earth, squared. But wait a second. G, mass of the Earth, radius of the Earth, that's just 9.8 meters per second squared. So we end up with 1/2 times the original acceleration due to gravity of the Earth. So if you have twice the mass, you'd expect twice the gravity force, but with twice the diameter, twice the radius, you have a factor of 4 in the denominator, so it's actually going to be 1/2, like we see here, 1/2 of the overall gravity acceleration, thus half the weight, so it's going to be half. So that's the second choice. Hopefully you see how that's done. Okay, we've got a couple more problems. Hope that makes sense. Question 19. A car with mass 1,000 kilograms has an engine with 50 kilowatts of power. If the car starts from rest and uses all of its engine power, how fast will the car be traveling after 4 seconds? There's a couple ways to do this problem, but this is how power relates to energy and kinetic energy and stuff like that. So power is the same thing as work divided by time. You could also say it's the rate at which energy is used per unit time. It's energy efficiency. The work that is done changes the kinetic energy. So this is 1/2 mv squared over t. And the question is, how fast will the car be traveling after 4 seconds? So we're looking for the velocity v. Well, I should multiply by time. So that's pt equals 1/2 mv squared. I should multiply by 2. That's 2pt equals mv squared. Divide by m, then take the square root. So this is v equals square root of 2pt over m. So p is power, t is time, m is mass. We got a factor of 2 in there and a square root. So let's put all the numbers in. So we've got 2 times the power. Now be careful. This power is in kilowatts. It needs to be in SI units of watts. So that'd be 50,000 watts because it's kilowatts. The time is 4 seconds. All right? Then divide by the mass of the car, which is 1,000 kilograms. Let's see how much I can work this out without the calculator first. 50,000 divided by 1,000 is just 50. 2 times 4 is 8. 8 times 50. So 8 times 5 I know to be 40. So that's the square root of 400. And the units would be meters squared over seconds squared in there. If you square root that, you just get meters per second. So that's going to be 20 meters per second on the nose. I didn't even need the calculator. 20 meters per second, the third choice down. Hope that makes sense. By the way, there are other ways you could have done this problem, but I think this is the most straightforward way. This was power interpreted in terms of work and time. You also could have said power is force times velocity, but you'd have to figure out the force based upon Newton's second law. You'd have to figure out the acceleration, stuff like that, but you would get the same answer. All right, hope that makes sense. Question 20. A structure consists of 4 masses, 2 with mass m and 2 with mass 2m, held together by a very light, massless rods and arranged in a square of edge length L as shown. The axis of rotation is perpendicular to the plane of the square through one of the masses of size m as shown. Assume that the masses are small enough to be considered point masses. What is the moment of inertia of the object about the axis of rotation? This is our axis of rotation over here with this little x. So notice the radius right here is equal to 0. So I'm not even going to worry about this mass in this corner. But we want the moment of inertia about the axis of rotation. Let's assume each of these rods are unimportant. So we're just going to say ignore the rods. We're also told that it's a square and that each of these sides is L. Also, here's a question. What's the distance from this axis of rotation to this small mass over here? Now, hopefully you're aware of this, but if you put a diagonal through a square, the length of the diagonal is L times the square root of 2. That's because you form a 45, 45, 90 isosceles right triangle by putting a diagonal across a square. And that's going to be our distance needed for this last mass, the small m. Now, the whole moment of inertia is going to be treating each of these masses as point masses. So if I call this 1, 2, and 3, it's going to be like I1 plus I2 plus I3. You can just add them up for the total rotational inertia. But that's like 2m, because it's the mass here, and the radius is going to be L squared. Plus, now be careful, for the second one, it's mass m, but the distance is square root of 2 times L squared. And then let's go plus, for this last one, again, it's 2m, and then the distance is L squared. So that's 2ml squared plus 2ml squared. That's 4ml squared. And then if I square this square root of 2, that's 2. And then ml squared, because I squared the L as well. So that ends up being 6ml squared. And that should be the final answer. So that's the first choice. That's the moment of inertia about the axis of rotation in the upper left corner of the square. Okay, that's question 20. That concludes this Physics 1 exam. Thank you very much for your attention. I will see you in the next video.